Hello. In this video, we are going to talk about lines in three-dimensional space. More precisely, we are going to learn what are needed to determine lines and how to derive line equations in different formats. So, a line L in three-dimensional space is determined by a point, call it P naught, with coordinates x naught, y naught, z naught, and a vector, call it V, whose components are V1, V2, and V3. And this vector has to be parallel to the line. Okay, so what we need is, again, a point on the line and a vector which is parallel to the line. So let's see how we derive line equations given this information. I'm first of all going to draw a three-dimensional coordinate system. I name my x's. Okay. Then I derive a random line. So let's say our line L is this. Okay. And next, I mark on this coordinate system and on the line the informations that we are given. So we know that we have a point P naught, and we have a vector V which is parallel to the line. Okay, so now finding the equation of the line means that you have to find the equations which are satisfied by a random point on the line. So let's pick a random point whose coordinates are x, y, and z. So we are supposed to find equations satisfied by x, y, and z. So I first create these two vectors. So I connect the origin to the points P naught and P. So I call this vector R naught and this R. So from the picture, we observe the following. The vector R, using the parallelogram rule, is equal to the sum of the vectors R naught and the vector P naught P. So next, what we know is that the line is parallel to the vector V. So, and from the picture, we observe that the vector P naught P is on the line L. So it is also parallel to the vector V. The vector P naught P is parallel to the vector V. So this means that I can express the vector P naught P as a scalar multiple of the vector V. Then, if we put this observation in this vector equation, we are going to get that the vector R is equal to the sum of the vector R naught plus the vector T times V. So we have now one equation, and this is called here the vector equation of the line. And this is the main equation which will lead to the other formats of the line equation. So to obtain the other formats, all we have to do is substitute the components of the vectors in this vector equation. So let's write the components of the vector r. So the vector r, okay, it's the vector between the origin and the point P. So its components are x, y, and z. So please note the difference in notation. I use brackets to represent vectors, and I use parentheses to represent points. Okay, then let's write our vector r naught. So over here, it is the vector which is between the origin and the point P naught. So its components are x naught, y naught, and z naught. Okay, and we already know the components of the vector v, which are v1, v2, and v3. So if I substitute these in these components in my vector equation, I'm going to have x, y, z is equal to x naught, y naught, z naught plus t times the vector v, which is t times v1, t times v2, and t times v3. I multiply each component of v by t. Then from this we get three equations. X is equal to x naught plus t times v1, y is equal to y naught plus t times v2, and z is equal to z naught plus t times v3. Okay, so we have now a set of three equations. So this is this way of representing line. It's called parametric equations of the line. Now, there is one more way of representing the line. Now, if I solve each equation in these parametric equations for t, I'm going to have t equals, from the first equation, x minus x naught over v1. And from the second equation, I will have t equals y minus y0 over v2. And from the third equation, I will have z minus z0 over v3. Now, as all these three fractions are equal to the same parameter, we can say that x minus x naught over v1 is equal to y minus y naught over v2, and that's equal to z minus z naught over v3, which we know that all are equal to t. So this way of representing the line, it's called symmetric equations of the line. So now we have three ways to represent a line, either by its vector equation, or by its parametric equations, or by its symmetric equations. Now we are going to solve some exercises and find line equations. but before we do that, I would like to summarize the different formats of line equations. So we have already talked about the vector equation of a line, the parametric equations, and lastly, the symmetric equations of a line. Okay. Now, let's look at the questions. In this exercise, we want to find the parametric equations of the lines in the following cases. So, in the first case, we'd like to find the line equation through the point 1, 2, minus 1 and parallel to the vector I minus 2j plus 5k. So, as you see in this exercise, we are given all the information we need to calculate the line equation, and all the information are ready to use. So, we need the point, and the point is given. So, the equation of x in the parametric equations of the line is x equals x naught, which is 1, plus t times v1, which is the first component of the vector v, so times 1. In other words, it's 1 plus t. Now, the equation of y, it's the y component of the point, 2, plus t times the second component of the vector v, so negative 2. In other words, 2 minus 2t. Then, the equation of z, it is the z component of the point, negative 1, and plus t times the third component of the vector v, so it's negative 1 plus 5t. As you see, all the information are given. All we need to do is put them in the equations. Okay, in the next exercise, we again want to find the line equations, parametric line equations through the points P and Q. So, the information we need, it's a point and a vector parallel to the line. So, we are given 2 points, but not a vector which is parallel to the line. So, to find the parametric equations, we first need to create a vector which is parallel to our line. So, for these kind of exercises, it is always a good idea to draw a picture. So, and put on that picture the information that you are given. So, we are looking for a line equation, and what we are given is that there are 2 points on that line, P and Q. So, using these 2 points, I can create a vector which is parallel to the line. So, observe that, let me mark this in a different color. The vector PQ, which is on the line, is also parallel to the line. So, the vector PQ is parallel to the line. So, let's find the vector PQ. So, it is 3 minus negative 2, 5. 5 minus 0, 5. Negative 2 minus 3, negative 5. Okay. Then, to find the parametric equations, you have all the information you need. You have a vector which is parallel to your line, and you have 2 points which are on your line. Now, you are free to choose any of these lines to find the any of these points to find the equation of the line. So, I'm going to choose the point P. So, then the equation of x is going to be negative 2, so the x component of the point P, plus t times the x component of the vector PQ, 5. In other words, minus 2 plus 5t. Now the equation of y is the second component of the point P, which is 0, okay, plus t times 5. So, in other words, it's just 5t. And finally, the equation of z, that component of the point, 3, and plus t times negative 5, which gives us 3 minus 5t. So, those are the three equations which represent our line that we know pass through the points P and Q. Okay, now let's look at our next question. Again, we want to find a line equation. This time we are given the following information. We are given a point on the line, and we are given the fact that the line that we are looking for is parallel to another line. So, let's say that this is the line that we want to find. And let's call the line that we are given by its symmetric equations here in this green box, L prime. So, what we know is that L prime is parallel to the line that we are looking for, which is L. So, now we know that on the blue line we have a point 3 minus 2, 1, and from the symmetric equations of the line L prime, I can find a vector which is parallel to the line L prime. So, I'm going to mark this again in green. So, from the symmetric equations, I can say that the vector which is parallel to the line L prime is 2, minus 1, and 3. So, observe that the components of this vector are the denominators in the symmetric equations of the line. Because if you remember the format of the symmetric equations of the line, the denominators are made of the components of the vector which is parallel to the line. So, now, we know that V is parallel to the line L prime, and the line L prime is parallel to the line L. Therefore, the vector V is also parallel to the line L. So, vector V is parallel to L. We have a vector parallel to L. We have a point on the line L. So, we can find its symmetric equations. I'll do it in this corner. The x component of the point, 3, and then the x component of the vector, V, plus 2t. The equation of y component, minus 2, minus t. The equation of z, the point, z component of the point, 1, then plus 3t. In our next exercise, we are going to find the intersection of the line which is given in its symmetric equations, x minus 2 over 2 equals y minus 3 over negative 2, which is equal to z plus 1 over 7, with the coordinate planes. Okay, so the first observation is the following. If a line intersects with a plane then the intersection is a point. So this exercise asks us to find the intersection. Now, based on this observation, what we are looking for is in fact a point. So we have, as you know, 3 coordinate planes. Which are given by the equations x equals 0, y equals 0, and z equals 0. So in this exercise, I'm going to intersect this line L one by one with these 3 planes, and if there is an intersection, we are going to find the point where this line intersects with these planes. Now, first of all, intersection with the coordinate plane x equals 0. So, finding the intersection means finding the point which satisfies both equations. So the equation of the plane, which is x equals 0, and the equation of the line, which is given by these symmetric equations. So, and to do that, there are you can do that in many different ways. So based on how the equations are given. So in this case, since the equation of a line is given in terms of symmetric equations, and we know that all these fractions are equal to the parameter t, we are first going to find the value of the parameter at the intersection. So if you consider this parameter as time, what we will do is, first of all, we are going to find the time when the intersection will happen. And then, using that time, we will find the components of the point of intersection. So, I know that x equals 0. That's the equation of the plane. I plug that in the equation 0 minus 2 over 2, that's equal to t. So I find that at the time of intersection, the value of the parameter is -1. Now, using this information, I can find the other components. So y minus 3 over -2, it is equal to -1. And if you solve this, you have y minus 3 equals 2 and y equals 5. So we have found the y component of the intersection point. Then z plus 1 over 7, it is equal to -1. So z plus 1 is -7, and therefore z is -8. So the point of intersection is, okay, the x component, we know that it is 0, x equals 0, and the y component, we found it to be 5, and the z component is -8. Okay. Now, I'm going to do the same thing with the other 2 coordinate planes. So first of all, y equals 0. I substitute 0 for y in the equation of y minus 3 over minus 2 equals t. And then I find the value of the parameter, 3 over 2. As I said, this is the time of intersection. And then I use this to find the other components. So x minus 2 over 2 is equal to 3 over 2. So from this, x minus 2 is equal to 3. So x is equal to 5. And z plus 1 over 7 is equal to 3 over 2. So z plus 1 is equal to 21 over 2. And z is 19 over 2. So the point of intersection is x component is 5, y component is 0, and the z component is 19 over 2. Again, the last part of the question, it's the intersection with z equals 0. So I'm going to use now the third equation, and I substitute 0 for z in this third equation. So 0 plus 1 over 7 is equal to t, and we find the time of intersection with the coordinate plane z equals 0 to be 1 over 7. Now I substitute this in the other equations. So x minus 2 over 2 is equal to 1 over 7. And from this, we have x minus 2 is equal to 2 over 7. So x is equal to 16 over 7. And next equation, y minus 3 over negative 2 is equal to 1 over 7. So y minus 3 is equal to negative 2 over 7. Therefore, y is equal to, so 21 minus 2, 19 over 7. And the point of intersection is therefore 16 over 7, 19 over 7, and 0. Our next exercise is the following. We want to determine whether the following lines given by their parametric equations are parallel, or whether they intersect, or whether they are skew. So, before I start solving the question, I would like to explain you the notions of parallel, intersect, and skew. So, two lines are parallel if their direction vectors are parallel. So the direction vector is the vector which we have used to determine the line equation. Now, two lines intersect if we can find two parameters so that at these two parameters, the x, y, and z of L1 is equal to the x, y, and z of L2. In other words, x1t is equal to x2s. So here, x1 means the x of line 1, and x2 means the x of line 2. And y1t is equal to y2 of s, and z1 of t is equal to z2 of s. Now, lastly, L1 and L2 are skew if they are neither parallel nor intersect. So, no intersection. If they are not parallel, we call them skew lines. Okay, so we first start by checking whether these two lines are parallel or not. So the direction vector of L1, so I'm going to call it V1. It is given by the coefficients of the parameter t, so which are 3, 3, and 5. Now, for the direction vector of the line L2, we have 4, -2, and 7. So, to check that whether they are parallel or not, we need to check their cross product, so which I'm going to calculate using the determinant. Okay, so if we expand this determinant with respect to the first column, first row, we are going to have 3, 5, -2, 7, I, minus 3, 5, 4, 7, J, and plus 3, 3, 4, -2, K. Now, we finish this, we are going to have 31I. Now, I don't need to continue the rest of the calculation. Well, I don't have to continue the rest of the calculation. I will do it anyway, but we observe from our first determinant that this cross product is not going to be 0. So, which means that these two vectors are not parallel. So, but anyway, as I said, let's continue the calculation. We are going to have 21 minus 20, which is 1. And then we are going to have -6 minus 12, which is -18. Okay, so this vector is not a 0 vector. So V1 and V2 are not parallel. And as a conclusion, we have L1 and L2 are not parallel. So now, next, we check whether they intersect or not. So for that, as the definition says here, we are supposed to find the values of the parameters t and s so that all components x, y, and z of line L1 and L2 are equal. So for that, I'm going to use the first two equations, the equations of x and y, to find t and s. And then I'm going to check if the t and s that we find using the first two equations satisfy the third equation, the equations of z. So I set the equations of x's to equal to each other. So 1 plus 3t that's the x of line 1, is equal to the x of line 2, 3 plus 4s. Then the y of line 2, it's 3t, should be equal to the y of line 2, 6 minus 2s. Now, I solve this system. Okay. First of all, we have 3t minus 4s is equal to 2. And then 3t plus 2s is equal to 6. Okay. As you see, if I subtract the first equation from the second equation, I'm going to have 3t minus 4s is equal to 2, and 6s is equal to 4. And from this, I find that s is equal to 2 over 3. And using the first equation, we are going to find the value of t. So t is, okay, let's do it together. 2, first of all, 1 over 3 times 2 plus 8 over 3. So, which is 14 over 9. So the values of the parameters in order to have an intersection is t equals 14 over 9 and s equals 2 over 3. Now, at these parameters are the z components of the two line equal as well. So I will say z1 at this t, so 19 over 4. Okay, it is equal to 1 plus 5 times 19 over 4, which is, okay, this is 79 over 9. And z2 of s, so at the other parameter, so we have 1 plus 7 times 2 over 3, and this one here is equal to 17 over 3. Now, what we observe is that the z values at these two parameters are not equal. So, our conclusion is L1 and L2 do not intersect. Okay, now the answer to our question is, based on the calculations we have found that the lines are not parallel and they do intersect. So, our final conclusion, L1 and L2 are skew. Hello. In this video, we are going to talk about planes in three-dimensional space. To be more precise, we are going to learn what is needed to determine a plane equations and what are different forms of plane equations. So, a plane Q in three-dimensional space is determined by a point, so call it P naught, with coordinates x naught, y naught, z naught on the plane, and a vector, call it n, with components n1, n2, and n3, perpendicular to Q, and which is called a normal vector. So, with the help of these two informations, a point on Q and a vector perpendicular to Q, we will be able to determine the plane equation as follows. So, let's pick a plane. Okay. And on that plane, we mark the information that we are given. It is the point P naught, and then the vector n, which is perpendicular to this plane. Well, I can choose this vector n anywhere on the plane, but I can also in particular choose it at the point P0. So, next I place this plane in the Cartesian coordinate system, three-dimensional Cartesian coordinate system. Now, finding the equation of a plane means that finding an equation which is satisfied by a random point on this plane. So, let's choose randomly a point and call it P, whose coordinates are x, y, and z. Okay. So, to find this equation, we will first create some vectors. I'm going to first connect the point P naught to the origin and obtain the vector R naught. Then I will connect the point P, the random point that I have chosen, to the origin, and I will obtain the vector R. So, now we have, using these 2 points, P and P naught, another vector in the picture, which starts at P naught and ends at P, and using the parallelogram rule, this vector is R minus R naught. Okay, what is special about this vector is the following. Since it uses the points which are already on the plane, the vector R minus R naught is also on the plane. So, and we have also the other information, which is that the vector n is perpendicular to the plane, which means that it is perpendicular to any vector on the plane. And therefore, the vector n and the vector R minus R naught are perpendicular. Or orthogonal, if you like. Okay, so this means that the dot product of these two vectors, n and R minus R naught, is equal to 0. And this equation here is called the vector equation of a plane. So that's the first form of the vector of equation. That's the first form of a plane equation. Now, using the components of the vectors involved in this equation, we can find also what we call the scalar equation of a plane. So the components of the vector n are n1, n2, and n3. And the components of the vector r minus r0. Okay, so from the picture, we see that the initial point of this vector is p0, and the terminal point is p. So in fact, the vector r minus r0 is the vector p0, p. So we know the coordinates of each point. The coordinates of the point P is x, y, and z. And the coordinates of the point P0 is x0, y0, z0. So this vector has components x minus x0, y minus y0, and z minus z0. Okay. If I place them in this dot product, I'm going to obtain the following. So n dot product r minus r0, it is going to be n1, n2, n3 dot product x minus x0, y minus y0, and z minus z0. And which will be n1 x minus x0 plus n2 y minus y0 plus n3 z minus z0. So that's the dot product. Now we know that this dot product should be equal to 0. So the scalar equation of a plane is the following: n1 x minus x0 plus n2 x, y minus y0 plus n3 z minus z0 is equal to 0. Now that we have seen how to find plane equation, let's do some exercises about finding plane equations in different cases. Now, in this first question, we want to find the plane through the point P419, which is normal to the vector 1, negative 1, 2. So, if you remember, what we need for a plane equation is a point and a vector normal to the plane. And in this question, all the information is directly given to us. The point is here and the vector is here as well. So all we have to do is use these two information directly in the equation plane, in the plane of the equation. So now we have to use the components of the normal vector as coefficients, and then we do x minus the x component of the point, and then plus the y component of the normal vector times y minus 1, and plus the z component of the normal vector times z minus z coordinate of the point. So, and all this is equal to 0. Now, you may want to simplify this equation. So, we have 1 times x, negative 1 times y, so x minus y, and 2 times z. Those are all the variables. And then the constants, negative 4 plus 1 and negative 18. It's equal to 0. And if I simplify this one more step and move all the constants to the other side, So I will have plus 18, plus 14, which is 22, and minus 1, 21. Okay, now let's move to the next exercise. Again, we want to find the plane equation, this time through the point 3, 1, 2, and which is parallel to the plane 4x minus 9y plus z equals 3. So this time we are not given directly all the information we need to find the plane equation. We have the point, but we don't have the normal vector. So our first goal is to find the normal vector of our plane. Now, to do that, I'm going to use the plane which is given in the question. I know that this plane is parallel to the plane that I'm looking for. So let's say that this is one plane, and this is the other plane. So this plane, its equation is, let's say, the one given in the question, 4x minus 9y plus z equals 3. And this is the one we are looking for. Okay, now what we know is that these two planes are parallel, and from the equation of this plane, I can find the normal vector of this plane. And that normal vector's components are the coefficients of the variables. So it is 4, minus 9, and 1. And now, using the fact that these two vectors are parallel, these two planes are parallel, I can also say that this normal vector of this plane is also a normal vector of the plane that we are looking for. So I can use in my calculations the normal vector of the plane given in the question. Then the plane equation is, so 4 times x minus the x coordinate of the point, minus 3, plus negative 9 times y minus the y coordinate of the point, 1, and plus 1 times z minus the z coordinate, which is 2, is all equal to 0. And then if you want to simplify this equation, so variables at the beginning, 4x minus 9y plus z minus 12 plus 9 and minus 2 is equal to 0. And if we move the constants to the other side, we will get 4x minus 9y plus z is equal to 14 minus 9, which is 5. Okay, let's look at our next question. We again want to find a plane equation, this time through the point 3, 5, negative 9, and perpendicular to the line which is given by these parametric equations. So again, one more time, for a plane equation, we need a point and a vector normal to the plane. However, the normal vector is missing in the question. So our first goal is to find that vector, and we are going to find it using this perpendicular line to the plane. So we are going to draw a picture to get a better idea. So here is our plane that we are looking for, and here is the line L. So if you want, let's say that this is the intersection point, and then the plane, the line cuts the plane and goes down like this. So we are given the parametric equations of this line, so which means that we can find the direction vector of this line. So I'm going to call this vector D. So let me write in this corner D. It is direction vector of the line L. Okay, so the components of this vector are the coefficients of the parameters. So it is 1, 2, and 3. Now, since L is perpendicular to our plane, let's call it Q, the normal vector of the plane is equal to the direction vector of the line. So this means the normal vector and this here I have already explained the D, and this notation means perpendicular. Okay, so now we know our normal vector. It is 1, 2, 3. We have been also given the point. So the plane equation is 1 times x minus the x coordinate plus 2 times y minus the y coordinate and 3 times z minus the z coordinate of the point. And we can simplify this to x plus 2y and plus 3z is equal to, okay, 3 plus 10 and minus 27. So, which is minus 40. Okay, so let's move on to our next exercise. In this exercise, we want again the same thing, the plane equation, but this time we are given the information that our plane passes through these 3 points, P with coordinates 5, 1, 1, Q 1, 1, 2, and R 2, 0, 2. Okay, so we need a point and a normal vector on the plane, and what we are given is 3 points. So we need to create, again using these 3 points, a normal vector. So again, I'm going to draw a picture and explain you how to find the normal vector using these 3 points. So we have the point P, Q, and R. Let's say they are spread over the plane like this. And using these 3 points, I'm going to create 2 vectors. One vector whose initial point is P, terminal point is Q. Another vector whose initial vector is P and terminal vector is R. So we have the vector PQ using the coordinates of the points. I can find the components of this vector. It is 1 minus 5, negative 4, and then 1 minus 1, which is 0, and 2 minus 1, 1. That's our vector PQ. And our vector PR will be 2 minus 5, negative 3, 0 minus 1, negative 1, and 2 minus 1, which is 1. So, now that we have these two vectors, we are going to create the normal vector. And the normal vector is a vector which is perpendicular to the plane. But the vectors that we have created are vectors on the plane. So, the cross product of any two vectors is a vector which is perpendicular to both vectors in the cross product. So, the cross product of the vector PQ and PR will create a third vector which is going to be perpendicular to PQ and PR. But since PQ and PR are already on the plane, this cross product will be perpendicular to the plane. So our normal vector is going to be the cross product of PQ and PR. So let's find that. Have the unit vectors ij and k. Then I copy in each row one of the vectors. So I expand this with respect to the first row. We have 0, 1, negative 1, 1, I minus negative 4, 1, negative 3, 1, j, and plus negative 4, 0, negative 3, negative 1, k. So our vector n has components. Okay, negative 4 plus 3, which is negative 1. Oh, excuse me, that's the component I. So 0 plus 1 is 1. Negative 4 plus 3, which is negative 1. With this negative, it is plus 1. And the last component, it is 4 minus 0. So that's a 4. So we have our normal vector. We have been given 3 points. Now, to find the plane equation, you can choose any of these 3 points. It really doesn't matter with which one you work with. So I'm going to choose the point P. Then we will have 1 times x minus the x coordinate of the point P plus 1 times 1 minus the y coordinate of point P and plus 4 times z minus the z coordinate of the point P. That's all equal to 0. And if I simplify this, x plus y plus 4z is equal to 5 plus 1 plus 4, which is 10. In this exercise, we want to find an equation of the plane that contains the two lines L1 and L2, which are given by their parametric equations. Okay, our goal is again to find a plane equation. However, this time we are neither given a point on the plane nor a vector which is normal to the plane. And we need to find first these two things to compute the plane equation. So again, I'm going to use pictures to find what I'm looking for. So let's say that this is the plane that I want to find its equation of, and I have two lines on this plane. Now, let's say that this is L1 and this here is L2. Again, there could be another configuration of this plane and the lines. They might intersect, or they might be placed in a different way on the plane. But whatever picture you use, it doesn't matter, because all of them are going to lead you to the same conclusion. Since these lines are on the plane, their direction vector, let's say D1, which is parallel to the line L1, and the direction vector of line L2, they are both parallel to the plane. So D1 and D2 are parallel to the plane. And therefore, as in previous exercise, the cross product of these two vectors is going to give us a vector which is perpendicular to the plane. So D1 cross D2 is normal to the plane. So let's find that normal vector. The components of the direction vector of line 1, they are the coefficients of the parameters in line 1. So it is 1, 2, and 3. The components of the direction vector of line 2, components of the parameters in line 2, 3, 1, and 8. So the cross product is going to be the normal vector. So we calculate this, 2, 3, 1, 8 I minus 1, 3, 3, 8 j, and plus 1, 2, 3, 1 k. Now we got 18, 16 minus 3, so 13i, and then minus 8 minus 9, negative 1 j, and plus 1 minus 6, which is negative 5 k. So our normal vector has components 13, 1, and negative 5. Okay, now that we have our normal vector, next we are going to look for a point on that plane. Now, let me go back to my picture. I'm trying to find a point on this plane. Now, what I know is that these two lines are on the plane. So, I can easily choose a point on one of these lines. It doesn't matter if you choose your point from L1 or L2. Now, choosing a point means assigning a value to a parameter. So, if we want to choose a point on line L1, then we have to simply substitute a value for the parameter t in line 1. So, the easiest is to substitute 0 for this parameter. So, if I substitute 0 for t in line 1, I'm going to get the point 2, 1, and 0. So the point 2, 1, 0, which is on line L1, is also on the plane so we have our normal vector, we have a point on the plane, we can find the plane equation easily. (13 times x minus the x coordinate plus 1 times y minus the y coordinate and minus 5 times z minus the z coordinate, which is 0. So we have 13x plus y minus 5z minus 26 minus 1 equals 0. So 13x plus y minus 5z is equal to 27. In this exercise, we want to find the intersection of the line given by these parametric equations and the plane. So, to find the intersection of any two objects, we need to set the equations of these two objects equal to each other. But in this case, because of the way the equations are given, the line is given by the parametric equations and the plane is given by a Cartesian equation, we have to substitute the parametric equations of the line in the Cartesian equation of the plane and first find the value of the parameter. So, we have 2 times x, which is 2 plus t, and plus y, which is negative 1 plus 2t, and that's equal to 3. We solve this equation now for the parameter t. 4 plus 2t minus 1 plus 2t is equal to 3. And we have 4t and plus 3 is equal to 3. So this means that at the intersection, the value of our parameter is equal to 0. Now, when t is equal to 0, what are the values of the x, y, and z? For that, we use the parametric equations of the line. So the x will be 2 plus 0, which is 2. The y will be minus 1 plus 0, which is minus 1. And z will be negative 1 plus 0, which is negative 1. So, our conclusion is the intersection is the point 2, negative 1, negative 1.